Well, why don't we talk a little bit about the iron preservation theory, maybe a little more in depth, and some other things that we're considering. As you know, there are two predominant preservation theories being offered. The other theory, which was promoted for a while, was the biofilm theory. And then initially, in the very beginning, there was a contamination theory, but in order to have contamination of osteocyte cells in bone, particularly in a dinosaur bone, let's say, a dinosaur bone gets contaminated by invading osteocytes. I mean, that's preposterous because they'd have to crawl out of some other bone that was just dead or just died. A bird crashed and smashed his wing, and the bone cells crawled out, crawled across the dirt, crawled into the dinosaur bone, and took up residence. So yeah, no, the contamination theory, at least for osteocytes, didn't hold water for very long. But then the biofilm theory came along, and there were some very elegant experiments that Dr. Schweitzer's team conducted that showed that certain proteins that are only found in vertebrates, that are not found in bacteria, because biofilms are the remnants of bacteria, sort of a sugary goo that they produce to inhabit while they're colonizing an area. And the theory was that those biofilms later on, became the osteocytes, which we talked about previously. It's impossible. But certain proteins were found, like actin and tubulin and histone, which are DNA wrapping proteins. The DNA molecule gets wrapped up and forms these X's and Y's that we see. And those proteins that wrap up DNA, histones, were found by Schweitzer's team in the T-Rex. So there's been some very sophisticated work done showing that the original, or what we call endogenous molecules, are still present. But in terms of preservation, the only examples that have been offered are the iron preservation theory, and there's a specific terminology for it. I wrote it down somewhere, but let's see if I can remember it here. Transition metal catalyzed intermolecular cross-linking of structural proteins. Okay, what does that mean? That means basically that iron is freed from the blood cells or some other source. There's a lot of iron bound in ferritin, for example. So somehow the iron becomes free, and when it comes in contact with oxygen in water, it produces hydroxyl radicals, which are like scrubbing bubbles. I mean, if you picture spraying, a bathroom, a shower stall with scrubbing bubbles, it foams up. And so I kind of picture the iron coming out of the blood into the blood vessel. The air is in there because the body's decomposing and water is infiltrating. So all these scrubbing bubbles are forming, and they're going through and chewing up the tissue like Pac-Man. And a lot of papers show that. And so, but the thinking is that somehow these hydroxyl radicals go into the structural proteins, the collagen fibers and the elastin fibers that are in the vessel. And that's what this paper is discussing. It's not discussing the osteocytes. This is only discussing vessels, because the osteocytes have a whole different anatomy. They have the phospholipid bilayer membrane. The cell membrane is basically a fatty layer. And so hydroxyl radicals chew that up like butter. And so cells just are chewed up by hydroxyl radicals very quickly. So they're making progress trying to explain the preservation of vessels through this cross-linking. But one of the big problems is that only every third or fourth amino acid in these proteins is cross-linked with another amino acid. So you have those remaining 3 or 4 in there that are going to decompose through autolysis over time. In fact, Mary Schweitzer very early on commented that autolysis is a really difficult thing to get past because it starts immediately at death, and cells just disintegrate as a result of autolysis. So, as a tissue processing expert, I don't know why these cells are still here, but you can't explain their preservation based on Fenton reactions in hydroxyl ions going through and cross-linking proteins. It's just going to chew up the cells. The other preservation motif that's offered is this degradation that we talked about lipids into advanced glycation end products. So Other than those two things, there's nothing proffered by anyone that can explain why these soft tissues are not completely disintegrated, even as you say, after 10,000 years.